Alright, this section deals with the basics of functions and graphs. And in this particular section, what we're going to look at is how to find the domain and range of a function, determine whether a relation is a function, determine whether an equation represents a function, evaluate a function, graph functions by plotting points, and use the vertical line test to identify graphs. Now let's look at the first definition. We need to look at some terms here. Let's start off with the word relation. A relation is nothing but any set of ordered pairs. So any set of ordered pairs is going to be defined as a relation. And then the domain is always a set of all first components of the ordered pairs, and the range is always going to be the set of all second components of the ordered pairs. So the domain is just a set of all x coordinates in that particular relation, and the set of all the y coordinates in that particular relation is called the range. And in this particular problem, well, here's an example. Here we want to find the domain and range of this particular relation. Now this right here is a relation, because all we have here is a set of ordered pairs: 8, -5, 11, 9, -1, 6, 0, 5, 8, 6, and -5, -15. And here we want to identify the domain and the range of this particular relation. And by looking at this, you can see the range, the domain is a set of all the x coordinates, and each x coordinate is written one time. So your x coordinates are 8, 11, -1, 0. Now 8 is written. 8 is there again, but we only write each x coordinate one time, and then -5. So this represents your domain. The range is your y coordinates. In this case, -5, 9, 6, 5, 6, and -15. Now notice that 6 is your y coordinate that's repeated twice, but we only write that one time. So this represents your range. So do understand the difference between the domain and the range of any relation. It's a set of all x coordinates listed one time, and the set of all y coordinates listed only once. Alright, another example would be finding the domain and the range of this relation. In this case, we got 0, 9.1, 10 and 6.7, 20 and 10.7, 30 and 13.2, and 36 and 17.4. And we want to find the domain and the range of this relation. In this case, the domain, that's a set of all the x coordinates. In this case, that's 0, 10, 20, 30, and 36. That's considered to be your domain. Now for the range, that's a set of all y coordinates in this relation. That's 9.1, 6.7, 10.7, 13.2, 17.4. Okay, so pretty much understanding how to find the domain and the range of any relation. Okay, now let's look at some more definitions here. The next thing we'll look at is what a function is and what it looks like. Alright, a function is nothing but a correspondence from the domain to the range, such that each element of the domain corresponds to exactly one element of the range. In other words, a function, if you're looking at a set of ordered pairs, the x coordinate cannot be paired with two different y coordinates. Okay, that's the rule for a set of ordered pairs being a function. A function can have two different first components with the same second component. That means you can have two different x coordinates paired with the same y coordinates. And of course, a relation is not a function when two different ordered pairs have the same first component and different second components, as I stated earlier. Okay, so all functions are relations, but not all relations are functions. Now let's look at an example. Here we want to determine whether this relation is a function. Alright, now take a look at this first one. 1, 2, 3, 4, 5, 6, and 5, 8. That particular relation is not a function. The reason for that is 5 is paired with 6, and also 5 is paired with 8. Here you got the same x-coordinate paired with two different y-coordinates. That you cannot have. In this case, the relation in part A is not a function. Part B, we got 1, 2, 3, 4, 6, 5, and 8, 5. That would be a relation. That would be a function, because each x-coordinate is paired with only one y-coordinate. Now this is an example where you could have two different x-coordinates paired with the same y-coordinate. Here 6 is paired with 5, and 8 is also paired with 5. But you're only looking at the x-coordinates to see if you have an x-coordinate paired with two different y-coordinates. In this case, if that was the case, then you would not have a function. So part B, the relation in part B is a function. Okay. So pretty much you know how to identify what a function is through a set of ordered pairs. Okay. Next we'll look at functions that can be expressed in the form of an equation. In this case here, let's look at some more terms. The independent variable and the dependent variable. Here the independent variable is of course the variable that can be assigned any value from the domain. That's, usually it's going to be your x coordinate. It's usually going to be the x. If a function is in the form of y is equal to some function in terms of x. And x is usually the independent variable because we can assign any value from the domain. But the dependent variable is going to be the variable that depends upon what the independent variable is. That's usually your y. Because usually y will depend upon what x is going to be equal to. Now, a quick way to determine whether an equation is a function is this. If the exponent for y in any equation contains an even power, like y to the second or y to the fourth, then that equation will not define y as a function of x. Okay? If the exponent for y has an even power, then that particular equation will not be a function. And here we're going to look at a couple of examples. Here we want to determine whether the equation defines y as a function of x. Here we got 2x plus y is equal to 6. And if we look at this, 2x plus y equal to 6, the exponent for y is a 1. That's an odd number, so that's okay. So here, this would be a function. So we can say that 2x plus y equals 6 is a function. However, for x squared plus y is equal to 1, that would not be a function. And here's why. If you look at that exponent for y, it's a 2. That's an even number. So in this case, that particular equation is not a function. Okay. So x squared plus y squared is equal to 1 would not be a function. So do be familiar with how to identify a function from looking at just the equation itself. And that right there is the solution and the explanation of why those particular equations are not functions. Alright, now the next thing we'll look at is function notation. Okay. And in function notation, you have the special notation called f with the x inside the parentheses. It's actually read f of x, or we can read that as f at x, not f times x. as f of x or f at x. That represents the value of the function at the number x. And when we evaluate a function, we replace the independent variable with this given value. So when it's written in function notation with f of x, usually the number will be given inside the parentheses. And you want to replace that x with that value that's in the parentheses. And we're going to look at a few problems like that. Like this one. Let's say we have the function f of x is equal to x squared minus 2x plus 7. And we want to evaluate each of the following. And in part A, you got f of negative 5. So here I'll write the function f of x is equal to x squared minus 2x plus 7. And then we want to evaluate f of 5. That was part A. Okay. Now to evaluate that, we're going to replace each x in this particular function with 5. So here we're going to have 5 squared minus 2 times 5 plus 7. And then we're going to simplify this. 5 squared, which is 5 times 5, that's 25. Minus 2 times 5, that's 10, plus 7. Alright, 25 minus 10, that's 15. 15 plus 7, that's simply going to be 22. So the value of that function when x is equal to 5 will be 22. Alright, so that's part A. Alright, part B is this. We have the same function, f of x equal x squared plus 2x minus 2x plus 7, but this time we're going to evaluate f of x plus 4. It's whatever is in the parentheses that we're going to replace the x with. So each x will be replaced with x plus 4. So here, this is what we're going to have. X plus 4, quantity squared, minus 2 times x plus 4 plus 7. Here I'm replacing each x with x plus 4. And then I'm going to simplify this. Now the x plus 4 quantity squared, we're squaring a binomial. So we can use the rule for squaring a binomial. And that rule is this. We square the first term. X and we squared will be x squared. Plus 2 times the product of these two terms in the parentheses. X and 4, if you multiply those, that'll be 4x. Plus the square of the last term. 4 and u squared will be plus 16. Okay? Now you'll just have to go back to probably one of the preliminary sections to find out how to square a binomial. You always square the first term, and then there'll be 2 times the product of the two terms in the parentheses, and then the square of the last term. Now for this one, we're going to have to use the distributive property. So negative 2 times x, that's going to be minus 2x. Negative 2 times 4 plus 4 is minus 8. Then bring over the plus 7. And then we're going to simplify this. We're going to have x squared plus 2 times 4x, that's 8x, plus 16. Bring down minus 2x minus 8 plus 7. And then we're going to combine like terms here. There's nothing to combine with the x squared, so we'll bring that down. 8x minus 2x is 6x. So that's plus 6x here. 16 minus 8 is 8. 8 plus 7 is plus 15. And this will be as far as we would go with that problem. So the value of that function when x plus 4 is replaced for x will be x squared plus 6x plus 15. So that's how you'll evaluate something like this. Now part C is that same function, but this time you're going to evaluate f of negative x. And in this case here, you replace each x with negative x. So you have negative x, and that's squared, minus 2 times negative x plus 7. Now if we simplify that, negative x and u squared is negative x times negative x, which is a positive x squared. Minus 2 times negative x will be a plus 2x plus 7. And that's as far as we'll go with that problem. In this case, it'll be x squared plus 2x plus 7. Okay. So do be familiar with how to evaluate particular functions that uses function notation. Okay. All right, next we'll look at graphs as graph of functions. All right, the graph of a function is the graph of its ordered pairs. And all functions with equations of the form f of x is equal to mx plus b graphed as straight lines. And such functions will be called linear functions. Okay. And in this particular problem, we want to graph the function f of x is equal to 2x and g of x, which is equal to 2x minus 3 in the same rectangular coordinate system. And we want to select integers for x starting with negative 2 and ending with 2. And we want to find out how is the graph of g related to the graph of f. So in this case here, we'll look at this function f of x is equal to 2x. And then we got the other function g of x is equal to 2x minus 3. And what I'm going to do here is create tables. This is f of x. And this is for here x and then g of x. And we're starting from negative 2 and ending with 2. So here, negative 2, negative 1, 0, 1, and 2. And we'll do the same thing here for g of x. Alright, let's start with f of x. Each x will be replaced with these x coordinates. So we're going to be doing 2 times whatever the x coordinate is. So if x is negative 2, 2 times negative 2 will be negative 4. And if x is negative 1, 2 times negative 1 will be negative 2. X is 0, 2 times 0 is 0. If x is 1, 2 times 1 will be 2. And if x is 2, 2 times 2 will be 4. Okay, so what I'm going to do here is draw a coordinate plane. Okay, now in this case here, let's first plot these ordered pairs here. Negative 2, negative 4 is this. We go to the left 2 and down 4. And draw the point. Then the next one was negative 1, negative 2 will be to the left 1 and down 2. And then 0, 0, that's at the origin. And then 1, 2 will be to the right 1 and up 2. And then 2, 4 was to the right 2 and up 4. And then we draw the graph of that line, which is f of x is equal to 2x. Okay. Alright, now we got g of x is equal to 2x minus 3. So that means 2 times the value of x, and then we're going to subtract 3 from it. So if x is negative 2, we're going to have 2 times negative 2, which is negative 4. Negative 4 minus 3 will be negative 7. And then for x is negative 1, 2 times negative 1 is negative 2. Negative 2 minus 3 is negative 5. If x is 0, 2 times 0 is 0. Minus 3 is negative 3. For x is 1, 2 times 1 is 2. 2 minus 3 is negative 1. And for x is 2, 2 times 2 is 4. 4 minus 3 is 1. So those are my ordered pairs for g of x. So here we're going to go on this graph to the left 2 and down 7, which is down here. And then for negative 1, 5 to the left 1 and down 5. For 0, negative 3, that's to the left. We stay at 0, but we go down 3. And then for 1, negative 1 to the right 1 and down 1. And then for 2, 1 to the right 2 and up 1. So here we have the graph of this line. G of x equals to 2x minus 30. Now what's the difference between these two graphs? Alright, in this case here you can see the difference of these two graphs look like this. It's the same graph as f of x is equal to 2x. However, it's just shifted down 3 places. Here it's at 0, 0 for f of x equals 2x. But for g of x equals 2x minus 3, it's shifted down down 3 places. Okay? So this point has just shifted down 3 places. This point up here has shifted down 3 places. Okay? So that's the difference between f of x and g of x. We usually call the f of x equal 2 of x the parent graph. And then for g of x equal 2x minus 3, it's the same thing, but it's just shifted down 3 places. Okay? Okay, next we'll talk about the vertical line test. We've already talked about how to determine whether a relation is a function through a set of ordered pairs and through equations. Now, if you were given a graph of a equation, well, just a graph, you can determine whether or not that graph is a function by doing the vertical line test. And here's the rule. If any vertical line intersects a graph in more than one point, then that graph will not define y as a function of x. Okay? So if the vertical line passes the graph at more than one place, then that graph will not be a function. Okay? So if you look at these 3 examples here, we can easily use that vertical line test to determine whether or not those graphs represent a function. Here's graph A. The graph looks like this. Now you can draw the vertical line anywhere, either to the left or to the right, but it must only pass that graph only once. So if I draw a vertical line here, you can see that the vertical line passes the graph at only one place. Or I could draw it here. It's only passing the graph at only one place. So part A, this graph in A represents a function. Alright, the one in the middle, part B, this too is also a function. I can draw a vertical line here. It's only passing the graph at one place. Or even here, that graph represents it's only passing the graph at only one place. So that too is a function. However, for part C, this one is not a function. Here's the vertical line. It's passing the graph at 2 different places. So this particular graph would not be a function. Okay. So be able to use the vertical line test to determine whether or not a graph of any equation is a function. Okay. And there's one more thing I need to talk about is just identifying the intercepts from a function's graph. I won't talk much about it, but I'll just go ahead and mention it. The zeros of a function called f are the values for which f of x is equal to 0. In other words, if I had, let's say, I have a graph of a function y is equal to f of x that looks something like this. Okay. The places where the graph crosses the x-axis, we talked about this earlier in one of the sections, those are your x-intercepts. And those x-intercepts represent the zeros of the function, because those are the points where the graph crosses the x-axis. And that's where f of x will be equal to 0 for that particular function. Okay. Now, a function can have more than one x-intercept. So here we got 3 x-intercepts here. That's okay. But for it to be a function, it can only have one y-intercept. So this point up here, there's only one y-intercept. And you can only have one y-intercept in order for it to be a function. If it has 2 different y-intercepts, it's not going to be a function. Okay, so be mindful of that. Okay, so this will complete this particular section on some of the basics of the functions and graphs.